In this lecture, we will be looking at a type of time series model called an autoregressive one, or an AR1 process. YT is an autoregressive process if, simply put, YT is a weighted average of its past values plus a white noise term. So in this case, we're focusing on the AR1. We will later look at a more generalized version where we have an ARP. But the definition of an AR1, we have time series of epsilon sub i's, or epsilon sub t's, and these are a white noise 0 sigma squared process. Generally, we'll think of it as a weak white noise, and they'll have mean 0 and variance sigma epsilon square. And since they're a weak white noise, they are uncorrelated. We say that the time series y1, y2, y3, so on, or just yt in general, is an AR1 process if, for some constant parameters, mu and phi, we have yt minus mu is equal to phi times the quantity yt minus 1 minus mu, plus epsilon t for all t. Mu is the mean. Phi is what we will call the memory parameter. And we'll talk more about that in a moment. The epsilons, those reflect the effect of new information at time t. So that's your randomness, your white noise term. And the natural way to think of an AR1 is, how does YT differ from its mean? Well, the way it differs from its mean, it remembers how it differed from its mean yesterday. Think of t on a daily time scale. It can be on any time scale, but we can think of it as daily just to intuitively understand what's happening. How y differs from its mean today, it remembers a piece of how it differs from its mean yesterday, plus some random noise term that represents new information. And that's really the essence of the autoregressive process, is it remembers some part of itself. We have a few different cases. It turns out for these two parameters, mu doesn't matter. Mu can be anything, but the behavior and the key properties of the AR1 very heavily depend on phi. And we have three cases. The first case, phi equals 1. The second case, when the absolute value of phi is bigger than 1. And the third case, absolute value of phi is less than 1. And there's a couple ways you can think of this. One natural way, if we come back to the idea of memory, if you think of phi as memory on a percentage basis, it makes sense. It's kind of natural that the percentage should be smaller than 100%. Also, for the intuition, it's kind of a little bit more straightforward if you think of phi as being positive for this. But you can think of phi should remember somewhere between 0 and 100% of yesterday. Remembering all of yesterday is kind of the cutoff where things get bad. Here, it would be, you can think of it like remembering 110% of yesterday. And we can see that you run into problems when you have that, when your memory parameter in size is bigger than 1, and also when it's actually equal to 1. It's not a coincidence that these cases break into cases consistent with results for a geometric series. And we'll see that show up, but remember that if you have a geometric series, say the sum from n goes to 0, from 0 to infinity, of say a r to the n, or maybe we can write it in this case a phi to the n, we know this converges if and only if the absolute value of phi is less than 1. And we will actually see this play a role in this third case. So we'll delve into that, but again, it's really helpful to think of phi as memory. So it differs from its mean today by remembering a piece of how it differed from its mean yesterday. And again, this case of phi in size being less than 1 is the case that we will focus on. Let's look at the other two cases first. In the case where phi equals 1, so this is our AR1 defining equation. If phi equals 1, then we plug 1 in here, and you see that the mu's will cancel. Yeah, so the mu's go, and what's left is yt equals yt minus 1 plus epsilon t. And that's nothing more than a random walk model. So if we think of it at, say, time 1, time 2, time 3, suppose that we have this starting at 0. Then this equation here, we have yt minus 1 equals epsilon t. So this epsilon t is the increment going from yt minus 1 to yt. So you would pick up, to go to yt, you would take yt minus 1. So let's look at, say, this case, y1 is y0 plus epsilon 1. And the way we're drawing this, we said y0 was 0. And so think of this kind of a random walk scenario where you're looking down at this picture and you have a person walking from left to right. And so that first step is going to be, say, at maybe your epsilon t comes out here. So that'll be your epsilon 1. Then their second step might be a little bit of a step to the right, and your third step might be more of a step to the left, so on and so forth. And so this is a random walk. Again, the difference between successive values of the process yt is exactly the increment specified by this noise term. So like this distance here between these two would be epsilon 2. The distance between these two, epsilon 3. The distance between these two, epsilon 4, and the distance between these two, epsilon 5. So we have the random walk case when our AR1 has a phi of 1. In the case where the absolute value of phi is bigger than 1, remember we said from a memory perspective, this is like your process remembering more than 100% of its value yesterday. The issue is, in this case, you get explosive behavior. So think of it as, think of the case where phi equals 2. So today we remembered 200% of yesterday. But yesterday would have remembered 200% of the previous day. Notice that you'd have a 2 times a 2 or a 4. The issue is you have a non-constant variance. So if you compute the variance of yt, which is a standard homework assignment that you can work out, this is the expression that you get. And notice sigma, that's the sigma for the white noise term. So that's our sigma epsilon. That is fixed. Phi is fixed. So the only thing here that's changing is t. But that means the variance of y1, you have a phi squared here. For a variance of y2, you have phi to the 4th. for variance of y3, phi to the 6th. So the problem here is that the variance is increasing in time. That means, by definition, the process yt is non-stationary. Remember, even to be weakly stationary, you need to have a fixed mean and a fixed variance. In this case, we see from this expression the variance is not fixed. Therefore, y is non-stationary. But the explosive behavior comes from the fact that the variance is increasing exponentially. So if your variance is increasing exponentially, you're getting a wider and wider spread of values for y as time goes on. So if you were doing some type of modeling of maybe contagion or disease spread or something like this, this would be an appropriate model, but it doesn't show up really much in finance because of this explosive behavior. And really what we're going to look for with autoregressive processes are models for stationary time series. And that's where we get into the case that we will typically deal with, which is the case where phi in absolute value is smaller than 1. So if phi is smaller than 1, we can think of it in absolute value. If it's smaller than 1, think of that as the deviation of y from its mean today remembers a piece of its deviation from yesterday, deviation from its mean yesterday, plus that noise term. In this case, it's weakly stationary. Mu is the mean. And we now rewrite this in a way that we'll see why we call it autoregressive. So let's multiply out in this defining equation on the right-hand side here, and we have phi yt minus 1 minus phi mu plus epsilon t, and then we'll bring the mu over to the right-hand side. And if we do that, we can group things in terms of mu. So if we group things in terms of mu, we see we have a mu term here and here. And so that gives us a 1 minus phi times mu. And then we have a phi times yt minus 1, and then our epsilon t term. But if we rename these, if we call this entire constant beta naught, and phi we were to label as beta 1, then we have this new version of the defining equation for the AR1, where yt is beta naught plus beta 1 times yt minus 1 plus epsilon t. And this is nothing more than a regression where y is the dependent variable and yt minus 1 is the predictor. And notice beta naught and beta 1, you have two parameters in here. So you have two regression coefficients in terms of two unknowns. So you still have your 2 degrees of freedom in there when you do your regression. If you get beta naught and beta 1, then you solve for phi and mu. And we call it an auto-regression because y is regressed onto previous values of itself. Now we can delve into this a bit, and we want to derive this alternative way to write down in AR1 as what we call an infinite order moving average. So let's look at this. And we have, again, our defining equation here for the AR1. But now, let's rewrite this equation for the previous time. So take, instead of time t, replace each t with t minus 1. So we get y times t minus 1 is this constant plus phi times y times t minus 2 plus epsilon t minus 1. It's just a version of equation 8 at the previous time step. But once we have this, we can then do some algebra. We can substitute the right-hand side of 9 into yt minus 1 in 8. If we do that, then we get yt is 1 minus phi times mu plus phi times that expression that we have on the right-hand side of 9 going in for yt minus 1, which is quantity 1 minus phi mu plus phi times yt minus 2 plus epsilon t minus 1. And then we still have our epsilon t. And let's simplify this a bit. So we have one minus phi times mu plus phi minus phi squared times mu plus phi squared yt minus 2 plus phi epsilon t minus 1 plus epsilon t. So let's try and group some terms. First, we note that this phi minus phi squared, right, that's this term here, is multiplied by mu, but we also have another term multiplied by mu. So this becomes the quantity 1 minus phi plus phi minus phi squared, all times mu, plus phi squared times yt minus 2 plus phi epsilon t minus 1 plus epsilon t. And we see here that minus phi and plus phi cancel. So that step leaves us with this expression here. And notice we did a factoring here. This was our 1 minus phi squared. So we're factoring this 1 minus phi squared here as the difference of the two squares, which is 1 plus phi, quantity 1 plus phi times 1 minus phi. So with that, we have this expression that we've just derived. But we want to see where this goes, because we can do this again. We can take that defining equation for the AR1 and do the same thing that we did before, except instead of writing it down for time t minus 1, we write it down for time t minus 2. We substitute for yt minus 2 the right-hand side of equation 11 into that yt minus 2 term in equation 10. When we do that, we will get yt equals 1 minus phi, we'll rearrange things a bit, times mu times 1 plus phi, plus phi squared times this new expression we will be adding in, plus phi times epsilon t minus 1 plus epsilon t. And in our brackets, we put the right-hand side of equation 11, 1 minus t quantity times mu, plus phi times yt minus 3 plus epsilon t minus 2. And now we simplify a bit, and simplify mainly by multiplying out here. So first we still have our 1 minus phi times mu times 1 plus phi But now here we have phi squared times the quantity 1 minus phi times mu, plus phi squared times phi, or phi cubed, times yt minus 3, plus phi squared times epsilon t minus 2, and then the remaining terms that are outside of the brackets, phi times epsilon t minus 1 plus epsilon t. And we notice we can do something with these first two terms. Specifically, notice that 1 minus phi times mu is common to both. This means we can rewrite this term, these two terms, as the quantity 1 minus phi times mu plus the sum of this 1 plus phi term and phi squared. And so we have 1 plus phi squared. And for the rest of the terms, we have phi cubed yt minus 3 plus phi squared epsilon t minus 2 plus phi epsilon t minus 1 plus epsilon t. And we want to start to think about emerging patterns as we're going through this, because we can keep doing this. And let's compare this version of yt that we've just derived to the version here in 10. Well, let's look at this first term here. We see we have 1 minus phi, 1 plus phi mu. It looks like we have something very similar here. The difference is we added a phi squared to this 1 plus phi term. So we went from 1 plus phi in that term to 1 plus phi squared. Then instead of phi squared times yt minus 2, we have phi cubed times yt minus 3. And then we see we start adding phi squared epsilon t minus 2, phi epsilon t minus 1, epsilon. We see that pattern here. And we start to look at this and say, well, I bet you if we did this one more time, we would get 1 plus phi squared plus phi cubed in this expression. Here, we would get phi to the fourth yt minus 4. And then you'd get another term of phi cubed epsilon t minus 3. And that's in fact what you would get. So as we continue to iterate this, what you end up with is this term. If you do this n times, you get 1 plus phi squared plus phi cubed plus phi to the fourth, all the way up to phi to the n minus 1. This term here, when you iterate n times, will be phi to the n yt minus n. And then the remaining terms, you notice here we had done it twice, and so we were summing up these weighted noise terms up until time 2. Actually, sorry, we had done it 3 times. So n minus 1. We sum n minus 1 copies of epsilon t minus I, phi to the I. So let's just look at what these would be. So if I is 0, you have phi to the 0, or 1 times epsilon t. If I is 1, you get phi epsilon t minus 1. If I is 2, you get phi squared epsilon t minus 2. And you keep on going and stopping at phi to the n minus 1, e epsilon t minus n minus 1. So you can keep going, but the question becomes, what happens when n goes to infinity? And here we see the geometric series result, in that the dependence on phi being smaller than 1 in absolute value, but we actually see that in more than one place. First, because phi, and this is really important, in size is less than 1, this term here approaches 0. as n goes to infinity, this phi to the n is exponentially decaying to 0. Over here, as n goes to infinity, this is becoming an infinite sum. And this sum is a geometric series. And notice it's a geometric series where its ratio term, phi, in absolute value is less than 1. That is the defining characteristic for the convergence of such a geometric series. Since it converges to, we usually call it a over 1 minus r. A is the first term of the geometric series. In this case, if I is 0, we have phi to the 0 or 1. So this converges to 1 over 1 minus phi. So what we have here, if you look at this entire first term, you have 1 minus phi times mu. And then if you replace that sum with a geometric series, you have 1 over 1 minus phi, and voila, the 1 minus phi and the 1 over 1 minus phi cancel. All that remains is mu. The second term goes to 0, and the other term is an infinite sum, and this is when we get the infinite order moving average expression. So we have yt is equal to mu plus an infinite series of the previous noise terms. Well, the current noise term, really, and then all the previous noise term. So this version shows us that such a model, an AR1 model, extends to an infinite history because you have this infinite history of these noise terms which show up in y minus 1, y minus 2, y minus 3, all the way back. So when you use an AR1, you are assuming you have an infinite history because every yt depends on all of the past values. Now that being said, it doesn't take long for past values to have very insignificant roles in the value of yt simply because the weights are decaying exponentially. So remember, this phi is a percentage. In size, it's smaller than 1. And so the further back you go in time, the larger I gets, the larger the power of a number that's strictly between -1 and 1. And so that phi to the I is racing to 0. So you get less and less weight in the past. But this is the idea. This is what an AR1 looks like. And so you can think of it in really two ways. One in the defining way, when we looked at that initial definition here, in that yt remembers something about itself from yesterday. But the calculation we just went through was saying, picking up on the fact, well, if this is a defining equation and today it remembers something from yesterday, well, yesterday it remembers something about itself from the day before. And the day before it remembered something about itself from the previous day. And you go with that, iterating back infinitely in the past. So this is another way to write the AR1, but notice in this case, all of that past memory is lumped into this infinite sum term, which just has the noise terms. So in this version, you don't have a previous y value showing up. But this is really the key, one of the key time series models that we use for stationary time series. And we'll look at how we use this more later on, but noting that you have both parameters, mu and phi, this is a very handy tool for modeling time series when you want to build in some type of memory, in particular, memory from the previous value of the time series itself. So we will have several follow-up lectures to this, where we talk about properties of AR1, extension to ARP, and things we can do with these AR models in different settings. So I encourage you to watch the next video.